Good afternoon. I'm going to speak in English. Apologies for that, for all the French speakers. I'm Simon Lewis, and this is Mark Maslin. I'm an Earth system scientist, a plant ecologist by training, and Mark is a geologist by training, and now works on climatology, paleoclimatology. And we're going to talk about defining the Anthropocene. So the idea that human activity has changed enough processes that are large enough and over long enough timescales and with enough variety and magnitude that we might define a new geological epoch. And if there is a new geological epoch, if we're in that geological epoch, the Anthropocene, then there's a question of when it began. And we're really going to talk about work in 3 papers. So a paper we both published in Nature earlier on this year, where we go through the evidence of whether we are in a new geological epoch, and then describe how geological time units are defined, and then take signatures from evidence from human prehistory and history and mark that against the formal criteria for a new geological epoch and see where we are at the end of that process, which time periods in human history and prehistory, and which markers might define the beginning of the Anthropocene. So we'll go through those 3 parts, and then a little discussion on 2 follow-up papers to sort of re-examine some of the things that we said in greater detail. So what is the Anthropocene? I think some of the controversy about this is that people are discussing quite different things. So often it's just in use for storytelling about humans and human activity, and an increase in our environmental impacts over time. For some, it's a synonym for global environmental change or changes to the Earth system. For some, it's an informal term used by scientists as a geological time unit. And increasingly the discussion, particularly around the Anthropocene Working Group and our work, is about formally when we might be able to define that time period as a formal new geological epoch. And I think that controversy is around mixing up those 2 things. So we try and extract this formal part from these others and then bring it back together towards the end. So the question, are we in the Anthropocene? I'm going to hand over to Mark.
So the key question that we are going to pose is not whether we should have a human-driven geological period, because as we heard previously, this has actually been discussed for many centuries. What we want to say is, do we have the evidence to say that we have a geological period, and do we have that evidence? So what we did was just summarize in the paper some of the critical evidence that shows that humans, or humanity, is having the same effect as geological forces, such as a meteorite impact or plate tectonics. So on the top left, I point out that humanity fixes half the nitrogen from the atmosphere to make ammonia, to make fertilizer. The nitrogen cycle on Earth has not been this disrupted for 2.5 billion years. That's how much we're changing it. On the right-hand side is, of course, greenhouse gases, which we know CO2 in 100 years has increased by 40%, and methane has doubled. On the left-hand side, the bottom, 30% of the world's surface, land surface, is now used for human production or usage. Okay? That includes Antarctica. Okay? So if you think about, 1/3 of all the land is used just for us. And on the bottom right, we are entering the 6th mass extinction. The extinction rates that have occurred over the last 50 years are on the scale of mass extinctions. And so the next question is, how do we actually define the start? Oh no, sorry, Time Wars. You can tell we've done this many times. So I'm the geologist, and of course we have what we call the Time Wars. Anyone who's not from Britain won't recognise the police box and Doctor Who on the left-hand side. Okay? Right. This is 200 years of scientific endeavour. This is the geologic timescale. This is work by hundreds and hundreds of geologists to refine time, to be able to split it down to smaller and smaller periods, all of which are defined by major changes in the Earth system. And as you can see, the first 3 billion years are all purple on the right, and then we get to the yucky yellows where we are. The key thing is that almost all of those boundaries are defined by a stratigraphic marker or golden spike that was introduced earlier this morning. So, we are currently in the Holocene epoch, and the previous epoch was the Pleistocene. Epochs last about 1 million years, so we are at the start of a major period. And it's defined as starting 11,650 years before present. And by the way, before present is defined as 1950. Okay? So that's the present day, is 1950 for archaeologists and paleoclimatologists. Now the key thing is the epoch, the Holocene, isn't that different to any previous warm period or interglacial period. And mixed in with the definition, of course, French definition of the Holocene is, of course, humanity and the difference of this interglacial because of humans. But these are all politically negotiated definitions. So, revolution that occurred about 15 years ago, they threw out the Quaternary period out of the geologic timescale. Because, of course, there was no tertiary, so why should we have a Quaternary? It was thrown out. Interestingly enough, a rearguard action by Quaternary geologists basically fought and fought and fought until, grudgingly, it was reinstated in 2012. So this is a political system of defining time. They are the Quaternary period, which is defined by the start of the Great Ice Ages. And so in our summary in Nature, what we try to do is put all the previous definitions with the possible Anthropocene definitions. And here we are just summing up the increase in temperature and CO2 at the end of the last ice age, which is defined by deuterium excess in the Greenland ice core.
Great. I'm just going to say one more thing about this Holocene epoch. So defining a geological time unit. So you've got the Earth going from one state to another. So we've got this cool period going into warm period, interglacial. But within that sort of 15,000 years, 5,000 years of change, then we have to pick one point and one marker for defining the before and after. So we're going from one state to the other, as we are doing now from pre-human actions affecting the global environment to some new state sometime into the future, but we have to pick some kind of marker to go with that. And this is a very small change in deuterium, so an isotope of hydrogen that marks the warming after a cool period of the Younger Dryas. So it's just one marker in that long chain going from cool to warm. And that's the kind of marker that we're thinking about in terms of the Anthropocene. And I guess the other thing about this being political is that that 4.6 billion year history that scientists have chopped up, this is a human construct to help us think about time and negotiate such enormous spans of history. So of course it's a human construct, so of course there's some political elements inside that, but driven by evidence. So all those markers you saw in that yellow diagram are all these global stratotypes, section and points, otherwise known as a golden spike. So they're a single manifestation, so it's one place on Earth, one record at one point. That's what defines the marker, and then it's correlated with many other markers that globally that show this shift from one state to another. And if we take that, so on the left is the current geological timescale, and then we basically have two arguments two options if we're going to define the Anthropocene. We either have we slot in after the Holocene a new boundary and have the Anthropocene, or we can get rid of the Holocene. And our argument is that we ought to get rid of the Holocene because until humans came along changing the environment globally, then we did not, this was just a regular interglacial. It was no different. It's not going to last millions of years as an interglacial, which it would have to be an epoch. It's that the human activities that last, whose impacts would last millions of years would then define it as an epoch. So a downgrading to the Holocenian stage for the current interglacial before human activity becomes global may be the right way to go. So there is an alternative to these golden spikes, and this is global standard stratigraphic ages. And they're used for a really long time ago when the fossil record is not so good and the evidence is not so clear to define a single marker. So you might see a big change in the Earth system over perhaps hundreds of thousands, millions of years, and you might agree in a committee that this is the date you'll use to make the formal definition. So you could do that. And some people have proposed, including the Anthropocene Working Group, that actually we should revert to that because environmental signals, the changes that humans make as the Earth as a system don't happen in an instant but take some time to change. But there's all sorts of dates have been thrown out there, and it's very difficult to objectively say one date agreed by a committee is better than another date agreed by either the same committee or a different committee. So we think that this is not the way to go because these golden spikes are the preferred way of doing it, and that's what the last few decades have been going through to build up to replace those prior ages with actual golden spikes, so physical manifestations that could be measured by scientists. And then finally, it's going to be ratified, or it may be ratified, that through a series of committees to formally define a new geological time unit. So it goes through three stages, starting off with the recommendation from the Anthropocene Working Group, which should come in 2016.
So in many ways, this is a very good procedure because it's, as Steiger would say, it is slow science. This definition is not going to be made overnight, and it's not going to be made by individual scientists, but it will take perhaps 2, 3, 4, maybe even a decade before those decisions are made, if it is ever ratified. What we want to do in the next part is to actually define the 3 possible golden spikes that we discussed and why they could be useful for defining the Anthropocene period. Now, and at the end, if there's questions, we're happy to actually discuss the philosophical reasons why the Anthropocene is so important. So the first one that has been suggested is early agriculture. So agriculture developed independently at the end of the last ice age, at the beginning of the Holocene, and it developed, of course, in Central and South America, in Africa, in Eurasia, and then spread out. What Bill Ruderman noticed is if you compare the carbon dioxide records of previous interglacial, previous warm periods, they go high at the end of an ice age, and then they slowly drop down. Same with the methane records, goes high, slowly drops down. His genius was to notice that the Holocene did something odd. So when you look at, say, methane, about 5,000 years ago, it starts to increase. With CO2, it's slightly earlier, perhaps 6,000 years. And what he proposed, and is probably true, is that early farming, deforestation, started to affect atmospheric CO2 much earlier than we ever suspected. The spread of agriculture, particularly wet rice agriculture in Asia, then started to drive methane levels up. So this is the first global signal of humanity on the Earth. The problem is that when you put it on that sort of scale, wow, doesn't it look big? It's really important. Look how big the actual signal is. If you compare it, and this is where we've taken his diagram in Science that Valerie presented this morning, and we've just scaled it properly to what we've actually done. And you can see the megafauna extinctions between about 50,000 and 10,000 on all the continents. So as soon as Homo sapien got there, we basically killed off all the large mammals. You then see that agriculture spreads out through the world. And if you look at deforestation, soil erosion, CO2, and atmospheric methane, if you look at where they start to increase, compared with what we have done in the last 100, 150 years, it is minuscule. And so we argued that actually early farming is really important. It should be the Paleo-Anthropocene, but it doesn't have a really good golden spike. And actually nothing else in the Earth system changes at that time. Globalization.
Great. So, so in 1492, so we're going through different stages to see whether the geological evidence matches the criteria for a golden spike. And in 1492, Columbus arrives in the Americas. And he's essentially joining the Americas population and the Eurasian population that have been separated for at least 12,000 years. And one of the big impacts of that was the global exchange of species. So moving first human foodstuffs, then human commensals, so things that move around with humans, and then all sorts of other species got moved from one continent to another. And boats carrying ballast means that ocean basin water was transported from one ocean basin to another. So you've got this global homogenization of Earth species, including lots of useful foodstuffs, which completely transformed almost everyone's diet on Earth. So even in the remotest parts of the Congo Basin, they began to be eating cassava from South America. So you've got this big mixing up of species known by Alfred Crosby as the Columbian Exchange. So this is pushing Earth onto a new evolutionary trajectory. So these continents have been separated for 200 million years, as have all these species, and now you've got species growing on other continents, and that's an irreversible change. We're not going to undo all that biological change. So for example, earthworms in North America, if you go there today, dig up some soil, you'll find earthworms there. They're almost all European earthworms that came with the early colonists and their agriculture. We've transformed the biological integrity of each of the continent's ecosystems, which is now moving us onto a new evolutionary trajectory. It was really global trade very early on. So this is a completely blank slide with the shipping logs from the 18th and 19th century plotted on it. And because there were so many ships and they were hugging the coastline, you can see most of the Earth's landmass outline. And that's partly because at this time, China's economy was the trade was in silver. So silver from those mines in South America was going to China in exchange for manufactured goods. So you have this global circuits of trade starting in a century after Columbus arrived in the Americas. We call this potential golden spike of a decline in atmospheric CO2 with a low point at 1610, the Orbis hypothesis, Latin for world, because at this time you had global trade and the beginning of a global world system inside the Earth system. And what happened in terms of this globalization of species, there was also a globalization of diseases. And Columbus arrived, and smallpox arrived with the Europeans and a bunch of other diseases, and as we heard this morning, around 50 million people is the best estimate at the moment, died in the century following Columbus's arrival. You see an increase in carbon monoxide captured in Antarctic ice cores, which shows a decline in biomass burning, because nearly all of those 50 million people were farmers. And they ceased farming, and each was farming at least a hectare each to feed themselves and their families. So you had tens of millions of hectares of forest regrowing back in the tropics and subtropics fast at the same time. And about 50% of the dry weight of a tree is carbon. So that's taking out of the atmosphere several parts per million of CO2 from the atmosphere into vegetation as a result of this decline in population and the simultaneous ceasing of farming over a continent. So we can capture this in the ice core records and in delta 13 carbon from the CO2, which shows that this carbon that was coming out of the atmosphere was going into the land surface and not into the oceans. We can see it in methane, and at the same time there was a volcanic eruption in 1602, which provides dust in all the ice core sediments, all the ice core records from the Arctic to the Antarctic, which also provides a nice marker. So this has those several correlated global markers, because the coolest part of the Little Ice Age, around 1600 to 1650, was the only part of the Little Ice Age that was truly global from those paleoclimatic records. So we have a global event, short with a distinct marker at 1610, that low point in CO2. So with the species movement onto different continents, we have this long-term irreversible change, and we also have with the CO2 marker from the same event a precise marker to mark potentially the beginning of the Anthropocene. So this showing it a low point at 1610. Some of this has been a bit controversial because there's a kind of long causal chain to get from Columbus arriving to the dip in CO2, the temporary dip in CO2. And you can break it down into 4 parts, but they're all actually well documented individually. It's just few people had put them all together one after another. So we know that millions of people did die. There's a good record of this. We know that almost all of them are farmers at that stage. There's good archaeological evidence for this. We know that trees grow back from modern experiments if you abandon farming, and we know that tree growth removes CO2 from the atmosphere. So while the full chain is long, then each individual part is fairly well evidenced. So stage 3.
So a number of the members of the Anthropocene Working Group are keen on the Industrial Revolution as being the key kick-off point to the Anthropocene. And we took a look at this. So Neil Rose is in our department, and he has developed over the last 2 decades a beautiful proxy. These are carboniferous particles, which are spheroids, and they are produced by high-intensity burning in coal and fossil fuel power stations. And the interesting thing is you can actually show different shapes for different power stations. So you can find out exactly where your pollution is coming from. And he has this huge database, not just in Europe, but all over the world, looking at when these carboniferous particles are found in lake sediments. And as you can see, around the world, the big problem is that it's a diachrous time horizon. So the Industrial Revolution did not occur at the same time everywhere. So you can see that, of course, in the UK and Ireland, it occurs quite early on and then starts to really rise from 1950 onwards. Same with Europe and North America. But if you go into the Southern Hemisphere or you look at North Africa or Asia, it's much later. It is post-1970 when you get these wonderful signals. So for that reason, and because we are wedded to sticking to the geological science of actually having a GSSP, we noted the importance of this, but dismissed this as a possible date for the start. So the fourth one, and the other possibility, is the Great Acceleration, which is 1950s to the present day. Now, you could argue that the whole of the modern world started at the Bretton Woods Conference, the monetary conference that set up the United Nations, the International Monetary Fund, the World Bank. They defined the dollar as the world currency, and I love this, they actually tied it to $35 an ounce of gold. Okay? Now, you may say this was the beginning of all evils in the world, or not. I'll leave that to your own conscience. But it also, in the 50s, modern medicine and demography changed massively. People have argued that this possibly was due to long-term economic cycles because of technology innovation. It also has been argued that it is that post-war United States that had no damage from the war and therefore had an industrial base to develop from very quickly. So if we look from 1950, as I said earlier on, 3.5 extra billion people have been born and survived. Okay? So that's double the population from 1950 to the present day. The energy consumption, as you can see, starts to go up in 1950 massively. And we have a beautiful spike, which is the bomb spike. So when nuclear weapons were first tested in 1945, from then onwards, it affected the radiocarbon in the atmosphere. This is why the present day for paleoclimatologists is 1950, because that's the last date before radiocarbon becomes useless. Now, the interesting thing is, of course, by 1963, a partial test bomb treaty was agreed. So as you can see, the wonderful spike there starts to descend a year later from 1964. So right in the middle of the 60s, you have this wonderful peak, which could be your wonderful golden spike. Interestingly enough, some of the members of the Anthropocene working group decided that they wanted it to be 1945, which is actually the first nuclear bomb test in Arizona. However, we would suggest that that didn't really have an earth-shattering change with that one event. Also, with the Great Acceleration, if you take all the data that Will Seffen has put together to drive the debate about why the Great Acceleration is so important, we've normalized all the data and put it on a graph. What you see is, of course, that the atmosphere, ocean, and terrestrial, so the actual environment, is moving before we get to 1950, and you then see that things like the social and economic move afterwards. I'm always interested that one of his key markers for the economy is the number of McDonald's on the planet. So that's 1945, somewhere in the cloud of that data, and the big red spike is what we would suggest, if you want this to be your golden spike, then 1964 is a very good marker, which you can go and take from tree rings and actually measure the C14 and find that spike. I, slightly glibly, I'm not particularly happy with this because, of course, this would mean that my parents were born in a different geological epoch. There's also another problem. So yeah, in terms of the Great Acceleration and when there might be a good marker for that time period of rapid and larger environmental change. So the Anthropocene Working Group have published a paper saying that it should be a GSSA, it should be a chosen date of 1945. And we've said that we should choose the peak of radionuclide fallout because that's where we can measure it best, and we can see it in ice core records, in lake sediments, and in tree rings, and a few other kinds of records. So we've got this global marker which will last in certain sediments millions of years. So that I think the half-life of one of the radioactive iodine isotopes is 11.3 million. 11.3 million years. So that record is going to last a long time. So it may provide a good marker. We think, unlike this GSSA date of 1945. And after their paper came out, and after our paper came out,
then someone leaked to us from the Anthropocene Working Group a poll that they did of the Anthropocene Working Group about when they thought the best date for defining the Anthropocene was. And if you look at these, only 2 people said 1945 was the best date. So we think this is the lead author and the second author, the chair of the group and the secretary of the group. But there isn't even agreement within the group for the date that they publish that they think should be the beginning of the Anthropocene. So I think in terms of this debate, it's wide open, and much more work is required to be able to kind of narrow down these choices. So in response to kind of where we are, so we, in the Nature paper, we basically did this kind of part 1, which is take all the data that's out there and screen it against these golden spike criteria and see what falls out from that. And then there's a part 2 that hasn't been done yet. We started to try and do it in this Anthropocene review paper out in the summer, but it really needs the communities involved in the Anthropocene to work out what the criteria are to decide between alternative start dates for the Anthropocene, so that those are transparently published, and then we have the screening process, see what's left, and then we have a process for deciding amongst those different time periods, dates, and markers, which one might be the best in terms of defining the Anthropocene. And we need to make this as transparent and as objective as we can. So in our conclusions at the end of that paper, we think that there are 2 time periods that have this golden spike marking a before and then a golden spike and then moving towards a new state of the Earth system. And we think that the orbit spike works. We have global trade. We have a global movement of species. For the first time for 200 million years, these continents are reconnected with the homogenization of Earth's biosphere, which is going to leading to novel evolutionary pathways and changing Earth permanently, coupled with an exact marker of this dip in CO2 and a bunch of other markers around the world, coincident with the very coolest period of the Little Ice Age, which was global. We think the Great Acceleration also provides those criteria. It's clear that many of the changes that are happening now are going to last hundreds of thousands, if not millions of years, including some of the residues from the testing and actual use of nuclear weapons. That could be conveniently marked, although it's not a world-changing event in and of itself, by the bomb spike. So by this increase in radionuclide fallout, and then it's tailing off after the partial test ban treaty. So both of those work, and they are both slightly different from some of the previous kind of ways of looking at the Anthropocene. So many people originally were talking about the beginning of the Industrial Revolution, and we place it just before that time period just before, where it's actually more the beginnings of the modern world with global trade and capitalist social relations, and that this is the break point before we move into the Anthropocene, and it also would mark the last synchronous globally cool period before the very long-term warmth of the Anthropocene. So fits that dominant climate change narrative relating to the Anthropocene as well. And our last slide. So we've got these 2 markers, and we think that they both could work, and these 2 time periods, and they both need probably more work before either of them could become a formal definition of the Anthropocene. But we kind of lean towards the Orbis spike because of the permanence of that movement of species and the evolutionary trajectory of Earth after that. And we have quite a nice marker, and it avoids it being too close to the present day, when, as Mark said, it seems people born in 1960 being from a completely different geological epoch to now. you know, this places it that the modern world is a time of the Anthropocene rather than just this last few decades. Thank you very much.